Analyzing a complex dynamical system requires a return map, a mathematical rule where a topological space folds back onto itself. Today, we examine map R. To model map R, researchers use three different operators. Each one provides a different perspective on how the system evolves. The first two are the age-structured renewal operator, T, and the folded domain counting representation, R-DOM. The third is the BV transfer operator, or operator P. A central goal was to prove operator T and operator R-DOM are exactly the same mathematical object, described in different coordinates. While that equivalence is now established, the transition from these counting models to the density-based operator P remains an open problem. The two representational styles simply do not yet align. The counting hierarchy, operators T and R-DOM, works by tracking domain multiplicity. They record how many times specific regions of the state space overlap, regardless of how much those regions are stretched. Operator P uses the Begg density transport. It tracks the continuous physical spread, accounting for how the map stretches or compresses the density of points. This creates a divide. One side counts overlapping layers, while the other measures physical distribution. Since all three operators model the same map R, it is logical to expect that their core mathematical results, their eigenobjects, should be interchangeable. To find where that interchange breaks down, we must first confirm that the counting hierarchy of T and R-DOM is internally consistent. Proving this consistency requires showing that the intertwining equation, J-DOM of T equals R-DOM of J-DOM, yields identical results across the entire state space. The proof begins with the B atoms, the first set of atomic generators for the system. R-DOM slices the domain against the map's branches and projects those pieces forward. This projection matches the specific rule operator T uses for regeneration and seed launching. SymPy verification confirmed this as a symbolic polynomial identity. The two sides of the equation are identical expressions for every value of the variable b. This same identity holds for the C atom generators, confirming that the operators are intertwined at a structural level. This proves by operator T is the domain counting unfolding of R-DOM's dynamics. There are two ways of expressing the same counting process. The final step of the proof covers the A states, which govern the system's interior dynamics. For an A state excursion, every exit from the interior must land within a range defined by the multiplier, lambda. The math dictates that the landing value must stay below 1/2. This inequality sequence maps the exact boundary for every possible exit. This boundary determines whether the system transitions into a B atom or a C atom. Step-by-step iteration at 50-digit precision across 9 different seeds, including irrational numbers like pi, produced a maximum discrepancy of 6.68 times 10 to the negative 52nd. This result is consistent with floating point noise. With these calculations verified, the intertwining theorem holds across all generators. We can now formalize the relationship between these operators as a 3-tier hierarchy. Tier 1 and Tier 2 are mathematically identical representations of domain counting. Both tiers rely on the same counting measure Perron eigenvector. Tier 3, the density-based operator P, remains separate from this unified counting block. The challenge is determining if the Perron eigenvector from the counting tiers can be converted into the invariant density used by operator P. A simple way to test this connection is through a direct identification, treating the domain counting blocks as a direct substitute for the continuous density. This test fails. The counting grid and the density curve fail to align, revealing a persistent gap between the two models. The discrepancy is a mismatch in Jacobian length weighting. Operator P accounts for the way the map stretches the space, which changes the density of the points within it. The counting operators ignore this stretching. They only track how many layers of the domain exist at any given point. The factor lambda discrepancy is the permanent marker of where these two representations diverge. It is the signature of the Jacobian weighting that the counting operators do not carry. This result shows that operator P functions through a different mechanism than the counting hierarchy. Sharing the same underlying return map does not guarantee that the mathematical objects of one system can be simply identified with the other. The factor lambda mismatch identifies exactly what a conversion between these systems must account for: length and Jacobian weighting. Because the naive identification fails to account for this discrepancy, the focus of the research shifts away from direct measure identification. Resolving this will require the construction of a canonical length weighting operator to bridge the two representations. Establishing the equivalence of the counting operators was a necessary step, as it defined the technical boundary between domain counting and density transport.